Have you ever stopped to think about what really happens after a developer hits save on a line of code? Well, in this explainer, we're going to follow that code on its pretty incredible journey, all the way from a single laptop to a massive application that's available to millions of people all around the world. We're going to pull back the curtain on the key technologies that make this whole complex process even possible. So, what does it actually take to make that huge leap? How can we be absolutely sure that the code will run reliably, scale up without breaking a sweat, and update without causing any downtime, no matter where it's running? That is the core question we're going to be diving into together. Okay, so our journey starts by tackling a really fundamental problem, a classic headache, really, that has been frustrating developers for decades.
Oh yeah, you've probably heard this before, or, let's be honest, you've probably said it yourself. A developer builds an application, it runs perfectly on their own computer. But the second it gets moved over to a testing server, or worse, to production, it just breaks. This usually happens because of tiny differences in system libraries, dependencies, or just the configuration between all these different environments.
The solution? Well, it's to create what you could call a universal box for our application. And that is exactly where Docker comes in. It basically packages the app and all of its dependencies. We're talking the code, the runtime, the libraries, absolutely everything into a single isolated unit we call a container. The real magic here is that this container will run exactly the same way no matter where you put it. In this approach, it has a massive impact. It completely solves that dependency hell we were just talking about. It guarantees consistency all the way from a developer's laptop to the cloud. And it creates this perfect standard building block that's just tailor-made for automated delivery pipelines. CI/CD. So great, we've solved the packaging problem for one single piece of our app. But modern applications aren't just one big thing anymore. They're often broken down into lots of small, independent parts called microservices. And that can mean managing hundreds, maybe even thousands of these containers all at once. How on earth do you coordinate all of that?
Well, if our containers are the instruments in an orchestra, we now need a conductor. And this is exactly where Kubernetes enters the picture. It's the tool that's going to manage all of those containerized boxes for us.
Now, this is a really common point of confusion, but let's be clear. Docker and Kubernetes are not competitors. They are collaborators. Docker is the tech that actually builds and packages the container. It's what creates the box. Kubernetes, on the other hand, is the platform that manages and orchestrates all of those boxes at a huge scale. To put it as simply as possible, Kubernetes doesn't replace Docker at all. It takes over after the container is built. It handles all the really complex jobs, like scheduling where containers should run, scaling them up or down as needed, and just making sure the whole application stays healthy across an entire fleet of servers. So, to really understand how our conductor, Kubernetes, works, we need to get to know its instruments. These are the core building blocks that you'll be interacting with when you start to define your application in the Kubernetes world.
First up is the pod. Now, this is the smallest and most basic unit in Kubernetes. You can kind of think of it as a little wrapper around one or more of our containers. It gives them a shared network identity and lets them easily communicate and share resources, almost as if they were running on the very same machine.
Now, here's the thing. You almost never manage pods directly. Instead, you tell Kubernetes what you want using something called a deployment. A deployment's whole job is to make sure your desired number of pods are always up and running. If one of them crashes, the deployment just automatically replaces it. And what about when it's time to update your app? Well, the deployment handles that gracefully, rolling out the change with zero service interruption. That's how you get that sweet, sweet zero downtime. But this raises a really key question. Since pods can be created and destroyed at any time, their internal IP addresses are constantly changing. So how can other parts of your system reliably connect to them? The answer is a service. A service creates a single, stable network address that acts as a permanent front door for a whole group of pods. Okay, here's a crucial best practice. You should never hard code configuration data like API keys or database URLs directly into your container image. Kubernetes gives us two excellent tools for this. We have config maps for non-sensitive stuff, and then we have secrets for the really sensitive data like passwords, which gets stored much more securely. Doing this makes your application way more flexible and, of course, a whole lot more secure.
All right, so our application is packaged up, it's being orchestrated, and it's securely configured. But as our system grows, we're suddenly left with a mountain of configuration files, often written in this format called YAML, for all of our deployments and services and secrets. Trying to manage all of this across different environments, it gets complicated fast. Enter Helm, which is basically the package manager for Kubernetes. Just like Homebrew on a Mac or apt on Linux, Helm is here to simplify things. It bundles all of the related YAML files for an entire application into a single package called a chart. This means with just one simple command, you can install, upgrade, or even delete a super complex application, like a database or a monitoring stack. And this brings us to the next big evolution in automation, something called gitops. The idea is actually pretty simple, but it is incredibly powerful. Your Git repository, yeah, the same place you store your code, becomes the single source of truth for how your entire system is supposed to look. Then a tool like Argo CD runs inside your cluster and it's constantly checking, hey, does the live system match what's described in Git? If the answer is no, it automatically fixes it. So let's put it all together. What does this fully automated end-to-end journey really look like in practice? Let's trace a single change from a developer's keyboard, all the way to a live service in production. Okay, let's trace the entire flow. It starts when a developer pushes a code change to Git. Right away, a pipeline automatically builds a brand new Docker image and then updates a configuration file right there in that same Git repository. That's it. That's the developer's whole job. From that point on, Argo CD sees the change in Git and automatically updates the live application in the cluster to match it. There are no manual steps, just a fully automated and completely auditable workflow. And that brings us to our final thought. We've journeyed all the way from a simple line of code to a fully automated, self-healing system that's managed entirely by configuration in Git. So when the entire process of shipping software becomes this streamlined and this reliable, what does that free us up to build next? What kind of new possibilities does it unlock?